Welcome to class 23, Thermodynamics. This is the second to last class, so that's good news, right? So here we go. Entropy change in a control volume, control mass, excuse me. Entropy generation and the principle of the increase of entropy is what we're covering today. This is 3 sections in Borgnacki. Hopefully you will read some of this content, and this will, I will just be trying to help you navigate through some of it and not speeding. I'm not spoon feeding you, I hope not. So anyway, here's a what if scenario like we do. What if we have, we're moving between these two states, states 1 and 2, and to start with, we're going to have 2 reversible processes to make a completely reversible cycle. So we go from 1 to 2, and at the path of A, remember this is path dependent on I think this is a TS diagram. It should be a TS diagram. I guess it doesn't really matter whether it's a PV diagram or a TS diagram. So anyway, so by the definition of these of this right here, for these reversible cycles, you can see that they're equal to 0. But now let's add into the mix. Let's put in an irreversible path that's going between 1 and 2, and then compare it with a B. So let's say that we went up from 1 to 2 via C, but came back in B. When we do that, we find that we actually have less than 0, right? So that does not equal 0 because we have irreversibilities taking place. So if you subtract these two from each other, these 2 equations, this one above and the one below, you can see that the product here, or the portion from A, is going to be greater than that of C. Since path A is reversible, and since entropy is a property right here, we can define these things. Now just replace them with the entropy here and say, if that's the case right here, that the integral of this SDC is going to be greater than so the entropy is going to be greater than this change in heat divided by temperature, right? So I kind of misspoke if I said was talking about these things being entropy, while as they might be like the definition of entropy, they're only the definition of entropy for a reversible cycle, right? So and what they're saying right here, by the way, since this right here is a quantity, right? So this is the definition right here. Let me back up a second and make some marks onto this page. I think marks help mark things up, make it better. Here's the definition of SA right here. And that's because the definition of the entropy is based on having a reversible cycle. So this is, but that is not the definition. Like this right here is not the entropy, right? This is just the change in heat, the integral of the change in heat divided by the temperature through path C. But we do know that we get to that spot and that spot, right? The change of this actual, right? SA is going to be, delta SA, I should say, is going to be equal to delta SB, right? But also, it's going to also be equal to delta SC, because these things have are states, right? The endpoints are all that matters if we say this delta. The integral matters here. So that's by definition. So what we basically said is now, okay, that entropy, because of the different path, is always going to be greater than what we would find if we did that integral of the thing, right? So and that's sort of like one of the main things. So this is a general statement about the entropy equation for a control mass. And so here is the general statement right here, that the change in entropy is going to be greater than that change in temperature, this change in heat, or the incremental little heat divided by the temperature, or to say that the change in entropy is greater than that. That's really the second law, right? You can't get something for nothing's the first law. The second law is you can't even break even. So let's continue with the next section here and talk about this thing. Okay, so we're going to create a new thing we call del S, and generation. And that means we're generating entropy by the act of, well, just doing anything. It's just we can't even break even, so we're always creating entropy. So let's be on the lookout. Let's create an equation, the entropy generation in a process, which is necessary because there are no real reversible processes. If integrated, we can come up with what we can call the entropy balance equation for a control mass. And this is a good one to pay special attention to. This is the whole point of what we're doing here, and maybe an equation that will you will see again in thermodynamics 2. And I think this is a really good diagram to go along with it and this statement right here. So these three things we want to own. And it says a lot about the TS diagram, right? So in the temperature versus entropy diagram, if you're going to go to the right, if we're going this way right here, the ways that we do it are to have heat in or generating entropy. And the heat in is just the function of adding heat to a system, to a control mass. We go to the right because we added heat in, or because the nature of the process generated entropy. The only way we can go backwards left is if we take heat out, right? And it's negative because the heat is leaving. So by definition, that's why it's negative. So the only way we can go to the left is if we take heat out. Rules, things that were highlighted in the text that I wanted you to really hone in on is we can generate, but we can't destroy entropy. And you want to compare that to energy, where you can't create or destroy energy, but you can create entropy. But like energy, you can't destroy it either. So there are two ways in which entropy of a system can be increased. And I put back this thing again. We can transfer heat into the system, or we can have an irreversible process, which can be thought of as lost work. That's what you can, maybe connect in your brain that's what an irreversibility is, that we've lost some work along the way. And the only way to increase entropy, or decrease entropy, excuse me, the only way you can do that is to remove heat from the system. Any increase in entropy is always associated with irreversibilities, right? So you can't really go backwards. And the presence of irreversibilities will cause the work to be smaller than the reversible work, right? So there's not even a thing in existence called reversible work. You're always going to lose a little bit, and you could think of those irreversibilities as the consequence of doing any type of process. Change in entropy due to heat transfer is heat transfer across the control surface. But entropy generation due to irreversible processes happens within the control volume. So there's a big idea of where are these entropy generations taking place. Some of them are coming across the control volume, but then the one that's because of irreversibility is within the control volume. And here is a pictorial statement right here that here is a reversible process where the area underneath the curve matches up with either heat right here or with work. But when those are for reversible processes, but here are for irreversible processes, so they have the dashed line. So that means in irreversible processes that you can't get the work out of that. But at the same time, I have been involved with the PV diagram quite a bit, where we've used the area inside what we call the banana curve for work. But I think it is technically true that these will not match. So work for the PV diagram and the heat transfer for the TS diagram, those areas. This book is making this, putting a very strong point on that. All right, so the last section, and I'm going to keep on going because I'm at the 10-minute mark, and this is all boring stuff, I know, to you. But I do think you should be reading this and going through it. But let's, I'll keep going. Boom. All right, so entropy change in a control mass can either be positive or negative, since entropy can be increased by an internal entropy generation, right, because of the process, and either increased or decreased by the heat transfer, depending on which direction of that transfer. So this is the point of this is we want to make our boundary maybe really large and incorporate the world, right? So here we have two systems next to each other, and then a third system C, which is the world. So we want to try to kind of do like a quick accounting for where did the entropy go, right? So if we put together the energy balance for each of these systems, right? So if we're talking about, and this right here is like the accumulation. So this could be internal energy. You could just replace that by internal energy if you'd like to. What happens to the internal energy? Well, we have for A, right? So this is system A, and so we have heat coming in, QA. So that's positive. We have work going out, and so therefore that's negative, because that's by the definition here. But we can also have some heat that's being transmitted from A to B, and that's going to be QB, and it's negative because that's heat leaving. And then we could also have work coming in right here for WP, and that ends up being negative, negative, so it ends up being positive, right? And then you could do the same thing for B, right? And you're just keeping track of things that's coming in, right? So this is QB is now it's positive for this system because it's crossing the boundary, and work B is now negative because like it's typical of the conservation of energy, it's work leaving, so it has that standard negative. And then we have something that's leaving to go to C, right? So we have from B, we're exiting and going to C. And of course, that's negative because we've placed it right here. And then we also somehow we're getting, the world is giving us some work. So we have this right here. And then if we balance out to C, right? So now we have C as the world out here. And we have things that are crossing the boundary. So we have QC, and that's this guy right here. He's entering heat in to C, so he's positive. And then you have WA, right? So that's work. That's work in. So that's gonna be negative, negative. That's why that's a positive there. And the same thing for QA. It's leaving C, so it's coming in here. And then lastly, we have work coming in, which makes negative. All right, so we have all those sign conventions together, and if you add up all of these systems, the total, it should equal 0. Now, that's a conservation of energy in the world, right? So a lot of times we will expel energy. We didn't destroy it. It went to the world, so now we've equated it. But here is the difference for the entropy of this, right? So if we do an entropy balance for each system right here, so here's how the entropy has changed. And I should mention, let's see, let's come back to this main equation right there. This is what we were applying. We're applying, I think, I can't remember. I think it's equation 637, but I will write it out somewhere in my notes. I should have written it somewhere. Equation 637, I think. See, did I write it? No, you didn't write that. Yeah. I think it's equation 637, but that's the important one. All right, so let's write that, apply that to this. And well, what happens? Let's just say that here is the entropy that we've generated. We could say that some of these are reversible, maybe. Maybe we could say that right here. We have this guy and that guy going here. So here's where our heat, and we've divided by temperature right there. But we also have this generation, right? The entropy that's been generated by the processes that have taken place. And right, so the work doesn't enter into any of this, by the way, noticeably. And then the same thing, we do the same thing for B, right? Just this is only the heat that's crossing boundaries and the temperature. And then lastly for the C, and we can add all these up. But the things that cancel out are still these generations, right? So all of these right here are going to be the accumulation. So if you want to say, well, where did the entropy go? Well, it was created by like all of these places, but it also eventually it all kind of ended up in C. I guess that's the way that we would say it. So as a quick example, and we'll be done with this, an irreversible process, consider the heat process that goes on with energy flows from a high temperature to a low temperature. And in this case, whoops, what happened to that? Oh, interesting. Let me pause 1 second and see if I can fix my picture. Okay, I got the picture back. All right, so what was happening here is we have this outside temperature, and apparently it's higher than the lower temperature, so it's going from the outside in. So we have crossing from C to B and then back into A. We have this transfer of heat through the wall of, let's say, a pipe or something, right? So there's a different temperature fluid here, TO, and then it goes down to T. So if you take the energy equation, we note that the heat flux that's coming across these things right there in has to equal out, right? So let's see if I can get my pen back. All right, so this has to be true right here. Here's a conservation of energy, not storing any energy, and then we end up finding that we could just say, well, the in has to equal out, and therefore we just call it Q. But if we do the entropy equation, which is that when I think I called it 637. In fact, let's take a look. Let's take a sneak peek at the book. I think I have it open. So let's see. There's entropy here. I think it's down in this place. Let's see. There you go. There he is, 637. Right. So, like I said, just like I said right here. Right. This equation right there. Boom. That's the one we're going to apply to this. Right there. So we're applying to it, and we're saying if these are reversible, right? So example of irreversible process, but I guess you say all of the entropies if we're talking about including C right there. So the generation that's taken place right there. So what we could say is that T 1 over, you could see that this is the same, the heat coming, the same heat transfer that's going on there, and that we're taking the difference between those two, and TO has to be larger than T, and just for this kind of tells us that, yeah, our the generation of entropy because of this process has to be greater than 0. It can only be equal to 0 if for some reason we have a isentropic process. But it seems to me that you can't really be equal to 0 because unless you have a really small temperature difference, but because there is a temperature difference that the entropy will increase. So there is the lecture portion, longer than I think anybody really wants to listen to. But I think in conjunction with reading the book yourself, you should become more comfortable with the nature of what is this entropy stuff, and how are we going to use it? Well, how we're going to use it, you'll see. We've already done a little bit of it in the homework assignments, but let's do a little bit more in these next examples. So I will talk to you here in a second.